So 6.2, this is about buffers. I would recommend going through this and reading this, and I'm going to give you the highlights. So let's start with most biological fluids are going to be solutions, so they're dissolved in water, and their pH pretty much has to be maintained in order for things to survive. And solutions are going to maintain, a solution that can maintain a constant pH is known as a buffer. What just happened? Okay, I pressed that on accident. So basically, you can add a very small amount of a strong acid or a strong base to a buffer solution, and it will resist a change in pH. Take a look at the next page. Let's move this. Okay. Let's see. I'm just looking for the highlight here. Here we go. Generally speaking, a buffer solution is going to consist of a weak acid and its conjugate base. Usually they should be present in a significant amount. So the higher the concentration of each one, the better the buffer capacity, and generally you want them to be in equal concentrations. So let's talk about what an acidic buffer is first. It's pretty obvious. These are buffer solutions that are going to resist changes in the acidic region of the pH scale. Turn to the next page. Generally speaking, the hydronium ion concentration would be equal to the Ka times the concentration of the weak acid divided by the concentration of the conjugate base. Okay. What I would highlight here also is that the hydronium ion concentration of a buffer solution depends on the Ka value for the weak acid, obviously, and the ratio of the concentration of the weak acid and its conjugate base. Okay? If you have a ratio of 1, it means that the hydronium ion concentration in the buffer equals the Ka of the weak acid. I would definitely memorize this or understand that. Okay. And then for number 2, down here, if the weak acid to conjugate base ratio increases, then the hydronium ion concentration increases. And if the ratio decreases, the hydronium ion concentration decreases. Okay? And then there's a number 3. For number 3, it says if you dilute a buffer solution, you're just going to be decreasing, or I'm sorry, you're going to be changing the concentration of the weak acid and its conjugate base concentrations equally. So therefore, the ratio will remain constant. So that means the hydronium ion concentration, or the pH, will not change. When you dilute a buffer solution. Okay? Okay, let's take a look at a couple of things here. Let's bring this up. Okay, let's look at question number 2. Okay, so in a buffer solution that's got a weak acid and its conjugate base, they will react to neutralize any added acid. As a result, if you add a small amount of a strong acid to a buffer solution, what will happen to the ratio of the weak acid to its conjugate base? Will it increase or decrease? Huh? Increase. Okay. And that means that the hydronium ion concentration will increase slightly, and the pH will decrease slightly. Okay. Number 3, when we look at pairs of things that might be used to make a buffer solution, remember, we're looking for a weak acid and its conjugate base generally. So, can I rule out this one? HNO3, nitric acid, strong acid. Okay. How about the next one? KF and HF. Is HF a weak acid?
Yes.
Okay, so since this is a weak acid, and its conjugate base would be F-1, they simply put an alkali metal with it. So this would be considered a buffer solution. Does that make sense? Okay, and then the next one, HNO3, another strong acid. So this pair is out. Okay, HCOOH, isn't that formic? Okay, so this, and then the COOH is here with an alkali ion. Does that make sense? Okay, so this would be a buffer solution. How about this one here? Are either one of these a weak acid? Yes? Yeah. Is HSO4 -1 in the table for weak acids? Does that make sense? Yeah? Okay. So then that means once it loses the hydrogen, it gets SO4 -2, which would be its conjugate base, which is with an alkali ion. This is acceptable. Okay. The next one, I don't think these anions do not match. So this is out. Does that make sense? Okay. And the next one, HCl, is a strong acid. That's out. And the very last one, you've got H2PO4. That would be, I believe, a weak acid in your table. So they both have the same anion. That would be acceptable. Okay. Okay, let's go on to pH change after you add a strong acid to a acidic buffer. Let's come down here. And then when a small amount of strong acid is added to a buffer, whatever conjugate base you have present, it will react with the hydronium ions from the acid. So, for example, here we have the conjugate base of acetic acid, okay? And it will accept a hydrogen ion from hydronium, which is representing your acid, and then it will turn into acetic acid, which is your weak acid. Okay? So let's take a look at the next page. Since you're producing this weak acid, this is going to be what makes your pH drop below 7. Okay, take a look at the top of the next page. Okay, the top of the next page. We're going to convert all of the hydronium ions from the strong acid because remember, hydronium ions are the same thing as hydrogen ions, right? And this all came from the strong acid, and these are converted to the weak acid and water in that reaction. So since you are increasing the acetic acid concentration, then that is why your pH is changing. All right, let's take a look at the next section. Let's drop down to pH change after you add a strong base. Okay, so here if we add a small amount of a strong base, then whatever we have present in solution in terms of the weak acid, it will react with the hydroxide from the base. So here I have my base, and then acetic acid is my weak acid that I have present in the solution, and what happens is it will donate a hydrogen to the hydroxide, and then you're going to produce that conjugate base and water. Okay, so all of the hydroxide ions from the strong base will be converted to the conjugate base of the weak acid and water. So that means that this concentration of your weak acid will drop, but then your conjugate base concentration will increase, and then that will obviously change the ratio. So the buffer component ratio will decrease. Okay. All right, let's take a look at the next page. On the next page, they summarize what happens to a buffer solution here in this figure. Okay, so here we've got the effects on pH of adding a strong base or a strong acid to an acidic buffer. Okay, so here was your original buffer solution. You had equal concentrations of a weak acid with its conjugate base. Okay, here you'll notice that we have 0.1 molar and 0.1 molar of each. And then if you add a strong base, then what happens is now the hydronium ion concentration will fall and your pH will come up just slightly. Okay, and that's because you're going to have a higher concentration of the conjugate base as opposed to the weak acid. Okay. On the right-hand side, if you go ahead and add a small amount of a strong acid, then what's going to happen is the hydronium ion concentration will rise, your pH will fall slightly, you're going to have a slightly larger concentration of the weak acid than you will of the conjugate base. Okay. Okay, let's take a look at the practice problems. Okay, so what I want you to do is do problem number 1. Do A, B, and C, and let's see what you come up with. We'll just let it play for a second, and then I will hit stop. Okay, next page. So next page is about buffers that are in the basic region, and then we'll talk about buffer capacity. So far, so good.